In 2022 and 2023, the James Webb Space Telescope revealed galaxies so massive, luminous, and structurally evolved that they appear far too mature for their place in cosmic history. Formed within just a few 100 million years after the Big Bang, these objects challenge the timeline predicted by the Lambda CDM model, which holds that such complexity should take billions of years to emerge. At the same time, anomalies in the cosmic microwave background hint at something even deeper. Roger Penrose has identified unusual circular patterns, so-called Hawking points, that defy conventional inflationary theory. One interpretation is profoundly unsettling. Under conformal cyclic cosmology, our universe may not be the first. Instead, it could be the latest chapter in an endless sequence of cosmic cycles, where each beginning is merely the echo of a universe that came before. The standard cosmological model's fractures. The Lambda CDM model, lambda for the cosmological constant representing dark energy, CDM for cold dark matter, is the theoretical framework that has governed cosmology for roughly 3 decades. It is a remarkably successful model. It correctly predicts the large-scale structure of the universe, the acoustic peaks in the cosmic microwave background power spectrum, the abundance of light elements produced during Big Bang nucleosynthesis, and the accelerating expansion of space first detected in 1998 through observations of Type 1a supernovae. For most of the observational history of modern astronomy, every new instrument and every new dataset appeared to confirm it. The model was not merely adequate, it was triumphant. The core narrative of Lambda CDM runs as follows. Approximately 13.8 billion years ago, the universe emerged from an initial singularity of infinite density and temperature. Within the first fraction of a second, the universe underwent a period of exponential expansion known as inflation, stretching quantum scale fluctuations to macroscopic size and seeding the density perturbations that would eventually collapse into galaxies. After inflation ended, the universe was filled with a hot, dense plasma of quarks, leptons, and photons. As it cooled, quarks bound into protons and neutrons fused into light nuclei, and eventually, at around 380,000 years, the plasma became cool enough for electrons to combine with nuclei, producing neutral hydrogen and releasing the photons that we now observe as the cosmic microwave background. The universe then entered a period known as the cosmic dark ages. No stars, no light, just a gradually cooling gas of neutral hydrogen and helium, threaded by the gravitational influence of cold. Dark matter halos slowly accumulating mass. The first stars in this model ignited somewhere between 100 million and 400 million years after the Big Bang. They were massive, short-lived, and intensely luminous. Population 3 stars, formed from nearly pure hydrogen and helium, with no metals to facilitate cooling. The first galaxies coalesced around these early stellar populations and around the gravitational wells of dark matter halos, which merged hierarchically over hundreds of millions to billions of years. Galaxies as large and structurally complex as the Milky Way, which contains roughly 250 billion solar masses of stars, and a supermassive black hole of about 4 million solar masses, were expected to require several billion years of assembly time. These predictions were not arbitrary. They followed directly from measurements of the primordial power spectrum, the distribution of density fluctuations in the early universe, which were obtained with extraordinary precision by the Planck satellite, whose final data release in 2018 characterized the CMB temperature anisotropies at angular scales down to roughly 5 arc-minutes. Planck's measurements constrain the amplitude of primordial fluctuations, quantified as the scalar spectral index, approximately 0.965. The baryon density, about 4.9% of the total energy budget. The cold dark matter density, about 26.8%, and the dark energy density, about 68.3%. From these numbers, the entire history of structure formation was, in principle, calculable. Simulations such as the Millennium Simulation, Illustris TNG, and EAGLE translated these initial conditions into predictions for how galaxies should form, grow, and distribute themselves across cosmic time. Those predictions held up remarkably well until the James Webb Space Telescope began returning data in late 2022. The first hints of trouble came quickly. Within months of its first science observations, Webb had identified multiple galaxy candidates at redshifts above 10, corresponding to look-back times of more than 13.3 billion years, and placing these objects in the first few 100 million years of cosmic history. Several of these candidates, when confirmed spectroscopically, carried stellar masses that strained the Lambda CDM predictions. A galaxy at redshift 12, less than 400 million years after the Big Bang, should not contain more than a few billion solar masses of stars if structure formation proceeded at the rate the model implies. Some of the objects Webb found appeared to contain 10 times that amount. The fractures in Lambda CDM are not limited to galaxy stellar masses. They extend to the sizes of galactic disks, the metallicities of early stellar populations, the presence of what appear to be fully formed barred spiral structures at redshifts above 2, and the apparent abundance of quiescent, meaning star formation suppressed, galaxies at redshifts above 4. Each of these observations points to the same underlying tension. The early universe was more organized, more massive, and more chemically evolved than the model predicts it should have been. These are not isolated anomalies. They form a coherent pattern suggesting that either the initial conditions of the universe were dramatically different from what Planck measured, or the physical processes governing early galaxy formation operate on timescales and efficiencies that current models do not capture, or, most radically, the Big Bang was not the actual beginning of the causal history that produced the universe we inhabit. None of these possibilities is trivial. The first would require revising the interpretation of the CMB power spectrum itself. The second would demand new physics at the level of star formation, feedback, and dark matter coupling. The third would require abandoning the philosophical and physical assumption that has underpinned cosmology since Hubble, that the observable universe has a finite causal history with a definite starting point roughly 13.8 billion years ago. What the data from Webb has done, with increasing clarity over the course of 2022 through 2024, is force the field to take all three possibilities seriously, simultaneously. The Lambda CDM model is not broken in the sense that it predicts things that are straightforwardly wrong. It is fractured in the more subtle and ultimately more troubling sense that its predictions cluster systematically on one side of what is observed, always predicting structures that are less massive, less organized, and less chemically enriched than what the early universe appears to contain. Systematic offsets of this kind, sustained across multiple independent observational probes, are the signature of a model operating outside its domain of validity. The question facing cosmology now is not whether to patch the model, but how deep the required revisions must go. It is worth cataloguing these fractures with some precision, because their breadth is what makes the situation qualitatively different from past episodes of anomaly in cosmology. The small-scale structure problems, the missing satellites problem, the cusp core problem, and the too big to fail problem have been known since the 1990s and 2000s and have been partially addressed through baryonic feedback mechanisms. The missing satellites problem refers to the large discrepancy between the predicted number of satellite galaxies around a Milky Way mass host, hundreds, based on dark matter simulations, and the observed number, around 50 to 60, even after accounting for detection limits. The cusp core problem refers to the conflict between the cuspy central density profiles predicted by dark matter-only simulations, the NFW profile from Navarro, Frank, and White, and the chord profiles inferred from observations of dwarf galaxy rotation curves. The too big to fail problem refers to the fact that the most massive predicted subhalos in Lambda CDM simulations are too dense at their centres to host the Milky Way's observed satellite galaxies. They should have formed stars and been visible, but they are not. Each of these small-scale problems can be partially mitigated by invoking supernova feedback, tidal stripping, or reionization heating of dwarf halos. But the tension introduced by Webb's high redshift observations is structurally different. It is not a problem of having too many predicted structures that are not observed. It is a problem of having observed structures that are too massive, too early, and too organized to have formed within the predicted timeline, objects that should not exist under the model's own equations. This is a harder problem to solve with feedback physics because feedback generally acts to suppress structure formation, not to accelerate it. Invoking stronger feedback at early epochs, as some models have proposed, makes the small-scale problems worse, while offering only partial relief to the high redshift mass problem. The S8 tension adds a further dimension to this picture. S8 is a parameter that combines the amplitude of matter fluctuation sigma 8 with the matter density omega m in a specific way, roughly proportional to sigma 8 times the square root of omega m divided by 0.3. It characterizes the clumpiness of matter in the late universe, as probed by weak gravitational lensing surveys such as the Kilo Degree Survey, KIDS, the Dark Energy Survey, DES, and the Hypersuprime Cam, HSC survey. These surveys consistently find a value of S8 that is approximately 2 to 3 sigma lower than the value predicted by the Planck CMB data under Lambda CDM. This means the late universe is measurably less clumpy than the early universe's initial conditions, as extrapolated by the model predict it should be. Like the Hubble tension, the S8 tension is a systematic discrepancy between early universe and late universe probes. And like the Hubble tension, it has proven resistant to resolution through simple, systematic error corrections. Taken together, the Hubble tension, the S8 tension, the high redshift galaxy mass problem, the early reionization problem, and the small-scale structure challenges, these fractures form a pattern. The Lambda CDM model, calibrated to the CMB at the epoch of recombination, systematically overpredicts certain properties of the late universe and underpredicts the organization of the very early universe. A model whose predictions systematically deviate from observations in opposite directions at opposite ends of cosmic time is not merely experiencing random noise. It is exhibiting the signature of a missing ingredient, something that operated across the full span of cosmic history in a way that the model does not capture. Whether that missing ingredient is a modification of dark energy, a revision of dark matter physics, new early universe processes, or evidence for a pre-Big Bang cosmic epoch that set different initial conditions, is the central open question in contemporary cosmology. JWST and the universe breakers. The James Webb Space Telescope was designed with one of its primary scientific objectives being the detection of the first galaxies, the earliest luminous structures to have formed after the cosmic dark ages. To accomplish this, it was equipped with a 6.5 metre primary mirror composed of 18 hexagonal beryllium segments coated in gold, a near-infrared camera, NIR-CAM, sensitive to wavelengths between 0.6 and 5 micrometers, a near-infrared spectrograph, NIR-SPEC, capable of simultaneously obtaining spectra for up to 100 objects, and a mid-infrared instrument, MIRE, covering 5 to 28 micrometers. The telescope operates at the second Sun-Earth Lagrange point, approximately 1.5 million kilometers from Earth, where its sun shield, roughly the size of a tennis court, maintains the telescope's operating temperature below 50 Kelvin. These specifications were not over-engineered. They were the minimum required to detect galaxies at redshifts above 10. where all ultraviolet and optical emission has been redshifted into the infrared. What Webb found, beginning with its first deep field image released in July 2022, exceeded the most optimistic pre-launch expectations. The first results from programs including CEERS, Cosmic Evolution Early Release Science Survey, JADES, JWST, Advanced Deep Extragalactic Survey, and GLASS, GRISM Lens Amplified Survey from Space, identified dozens of high redshift galaxy candidates within months. When these candidates were subjected to spectroscopic follow-up, particularly through NIRSpec's multi-object spectroscopy mode, many were confirmed at redshifts placing them within the first 500 million years of cosmic history. The galaxy that most forcefully crystallized the tension with Lambda CDM in the early months of Webb's operation was not a single object, but a set of 6 galaxy candidates identified by Ivo Laber of Swinburne University of Technology and colleagues, reported in Nature in February 2023. These 6 objects identified in the Sears field had photometric redshifts between 7.4 and 9.1 and inferred stellar masses ranging from approximately 10 billion to 100 billion solar masses. The most extreme of them, if its redshift and mass were confirmed, would contain a stellar mass comparable to the present-day Milky Way, assembled when the universe was less than 700 million years old. Laber and colleagues noted that the cumulative stellar mass density implied by these objects exceeded Lambda CDM predictions by a factor of roughly 9 at the high mass end. The phrase universe breakers, coined in media coverage of this paper, was not hyperbole. It accurately described the implied magnitude of the tension. To understand why these masses are so problematic, it is necessary to understand the concept of the stellar mass function, the distribution of galaxy masses at a given epoch. In Lambda CDM, this function evolves predictably with time. At early epochs, massive galaxies should be extremely rare because insufficient time has elapsed for dark matter halos to grow to the sizes required to host them, and for the baryonic matter within those halos to convert into stars at high efficiency. The stellar mass density at redshift 10, predicted by the model, is several orders of magnitude lower than at redshift 0. The objects Laber and colleagues identified appeared to violate the predicted mass function at the high mass end by roughly an order of magnitude or more. Subsequent work attempted to reconcile these observations with the standard model through several mechanisms. One proposal invoked an elevated star formation efficiency in the early universe, a scenario in which early galaxies converted a higher fraction of their gas into stars more rapidly than present-day galaxies. Standard feedback models assume that supernovae and active galactic nuclei inject energy into the interstellar medium, suppressing star formation and limiting the efficiency with which gas converts into stars. If these feedback mechanisms were weaker or differently configured in the early universe, star formation efficiency could have been substantially higher. Some researchers proposed efficiencies approaching 30 to 50% in the most extreme halos, compared to the roughly 10 to 20% typical of present-day massive galaxies. Another proposal suggested that the photometric redshifts of some of these objects were overestimated, that bright low redshift interlopers, whose spectral energy distributions mimicked high redshift Lyman break galaxies, had contaminated the sample. This is a legitimate concern in photometric surveys. The Lyman break technique, which identifies high redshift galaxies by the sharp drop in flux shortward of the Lyman limit at 912 angstroms, redshifted into the optical or near infrared, depending on the galaxy's redshift, can in principle be confused by heavily dust-reddened galaxies at lower redshifts or by galaxies with unusual spectral features. However, as spectroscopic confirmations accumulated through 2023 and 2024, the contamination hypothesis became increasingly untenable for the brightest and most extreme objects. A third, More radical interpretation emerged from researchers including Mike Boylan-Colchin of the University of Texas at Austin, who argued that even the most generous adjustments to star formation efficiency within Lambda CDM were insufficient to account for the most massive objects. His analysis, published in Nature Astronomy in 2023, showed that several of the confirmed high redshift massive galaxies exceeded what he termed the maximal galaxy limit, the theoretical maximum stellar mass achievable if every baryon in a dark matter halo of the predicted size were converted into stars with 100% efficiency. Objects that exceed this limit are not merely challenging for the model, they are, within the framework's own assumptions, impossible. Their existence implies either that the halo mass function at high redshift is wrong, meaning the initial conditions of the universe need revision, that the cosmological parameters inferred from the CMB are inaccurate, or that some entirely unaccounted physical process accelerated structure formation beyond what any current model anticipates. The universe breakers, in this sense, are not simply outliers. They are diagnostic probes of the initial conditions of the universe. Each confirmed extreme mass galaxy at high redshift constrains the possible explanations more tightly and pushes the required modifications to the standard model further from the comfortable realm of minor parameter adjustments into the territory of fundamental revision. The Boylan-Colchin analysis was particularly significant because it framed the problem in terms that allowed no escape through parameter adjustment. The maximal galaxy concept, the absolute upper limit on stellar mass given the baryon fraction of a dark matter halo, and a 100% star formation efficiency, is model independent in the sense that it requires only the cosmological baryon fraction, approximately 0.156 from Planck, and the predicted dark matter halo mass function. If observations return stellar masses above this ceiling, no model of star formation physics can rescue the standard cosmological framework. The required revision must be at the level of the halo mass function itself, meaning the primordial power spectrum, the cosmological parameters, or the nature of dark matter. Subsequent spectroscopic campaigns from the JADIS program, described in a series of papers through 2023 and 2024, by a team including Daniel Eisenstein, Harvard, Nora Lutzdorf, ESA, and Brant Robertson, a UC Santa Cruz, provided the most comprehensive census of high redshift galaxy properties yet obtained. The JADIS program allocated approximately 750 hours of NIR spec time to obtain spectra for more than 700 galaxy candidates at redshifts above 4. Within this sample, the team confirmed multiple galaxies at redshifts above 10, with stellar masses above 10 billion solar masses, and identified a statistically significant excess of massive galaxies relative to the predicted mass function at the high mass end. They also found that many of these early galaxies had specific star formation rates, star formation per unit of existing stellar mass, that were substantially elevated compared to model predictions, consistent with a picture in which early star formation was both rapid and efficient, beyond current theoretical expectations. The galaxy JADIS GS Z14-0, spectroscopically confirmed at a redshift of 14.32 in a paper published in 2024, pushed the observational frontier further still. At this redshift, the universe was approximately 290 million years old. The galaxy had an estimated stellar mass of several hundred million solar masses, not the most extreme object in the Webb sample, but at a redshift where the Lambda CDM model predicts that even halos capable of hosting galaxies of this mass should be extraordinarily rare. The probability of finding such an object in a survey of the sky area covered by JADIS under the standard model was estimated at a level suggesting either exceptional luck or a systematic excess of massive high redshift galaxies at a level an order of magnitude above predictions. What these objects collectively establish is not a single anomalous discovery, but a population-level statistical excess. Statistical excesses at the high mass end of the galaxy mass function at high redshift, sustained across multiple independent surveys with independent instruments and analysis pipelines, cannot be attributed to systematic measurement errors in any single program. They constitute a genuine scientific tension that demands a physical explanation. The Lambda CDM model, as currently formulated, does not provide one. Chapter 3. JADES-GS-11 and Reionization. Among the specific objects Webb has returned to the scientific literature, JADES-GS-11 stands out not only for its extreme distance, but for what it reveals about the physical conditions of the early universe during one of its most consequential transitions. The galaxy was first identified in Hubble Space Telescope imaging and designated as a candidate at redshift approximately 11, placing it roughly 330 million years after the Big Bang. Webb's NIR spec confirmed its redshift at 10.6, corresponding to a look-back time of approximately 13.4 billion years, making it one of the most distant spectroscopically confirmed galaxies known at the time of its confirmation in late 2022 and subsequent detailed publication in 2023. What made JADES-GS-Z11 scientifically extraordinary was not simply its distance. It was the detection, in its spectrum, of a strong Lyman alpha emission line. Lyman alpha radiation is produced when hydrogen atoms transition from the first excited state, n equals 2, to the ground state, n equals 1, emitting a photon at a rest wavelength of 121.6 nanometers in the ultraviolet. In a neutral hydrogen medium, Lyman alpha photons are resonantly scattered with extremely high efficiency. The cross-section for this interaction is roughly 4 times 10 to the power of minus 14 square centimeters at the line center, making the intergalactic medium essentially opaque to Lyman alpha radiation when the neutral hydrogen fraction exceeds approximately 10%. During the epoch of reionization, the period when the first generations of luminous sources ionized the surrounding neutral hydrogen, transforming the intergalactic medium from predominantly neutral to predominantly ionized, the universe's neutral fraction was by definition high. The standard model of reionization, informed by observations of the Gunn-Peterson trough in quasar spectra and by constraints from the Planck optical depth measurement, places the midpoint of reionization at a redshift between 7 and 8, with reionization largely complete by redshift 6, approximately 900 million years after the Big Bang. At redshift 10.6, the universe should have been overwhelmingly neutral, with a neutral fraction approaching unity. Under these conditions, any Lyman alpha photons emitted by JADES-GS-Z11 should have been immediately absorbed by the surrounding intergalactic medium, never reaching a distant observer. The detection of Lyman alpha emission from JADES-GS-Z11 therefore presented an immediate problem. The lead author of the study describing this detection, astronomer Joris Wittstock of the University of Cambridge, was direct about the surprise this result represented. The observed Lyman alpha equivalent width, a measure of the line's strength relative to the continuum, was substantially above what models of reionization predicted should be observable at that redshift. The line was not weak or marginal. It was clearly detected, with a signal-to-noise ratio sufficient to rule out instrumental artifacts. The resolution proposed by Wittstock and colleagues involves the concept of an ionized bubble, a region of the intergalactic medium that has been cleared of neutral hydrogen by intense ionizing radiation from the galaxy itself. If JADES-GS-Z11 was sufficiently luminous in ionizing ultraviolet photons, it could, over a sufficient timescale, have carved out a bubble of ionized gas around itself large enough for Lyman alpha photons to travel some distance before encountering neutral hydrogen. Once the photons travel far enough from the galaxy, they are redshifted out of the Lyman alpha resonance frequency and can pass through the remaining neutral gas. The analysis by Wittstock's team concluded that the bubble around Giardia's GS-Z11 must extend approximately 650,000 light-years in radius to explain the observed Lyman alpha transmission. A bubble of this size, created 330 million years after the Big Bang, implies an extraordinary ionizing photon output. The galaxy's inferred star formation rate and ultraviolet luminosity are consistent with an ionizing photon production efficiency substantially above typical values. One possible explanation is that Giardia's GS-Z11 hosts an unusually hot and luminous stellar population, perhaps a significant contribution from population 3 stars or from stars accreting mass from companions, which can substantially enhance their ionizing output. Another possibility, raised in subsequent analysis, is that the galaxy harbors an active galactic nucleus, a growing supermassive black hole whose accretion disk produces a hard ultraviolet spectrum capable of ionizing surrounding gas more efficiently than stellar populations alone. The co-author of the original Wittstock study, Kevin Hainline of the University of Arizona, expressed the scientific community's reaction to this object with notable directness. A galaxy of this kind should not have been found at this epoch under the assumptions of standard reionization models. The detection does not merely require adjusting the timeline of reionization. It requires acknowledging that individual galaxies in the early universe were capable of locally transforming their large-scale environment, carving ionized channels through the neutral intergalactic medium, substantially earlier than the global reionization process reached completion. This has significant implications for understanding which sources drove reionization. Pre-Webb models generally assume that reionization was driven by a large population of faint, low-mass galaxies, on the grounds that massive bright galaxies were too rare in the early universe to provide sufficient ionizing photons over the required volume. JADES-GS-Z11 and objects like it suggest that at least some massive, luminous galaxies were present early enough to contribute significantly to reionization, and that their local ionizing impact may have been dramatic. If the population of such objects is larger than the standard model predicts, then the timeline, topology, and driving mechanisms of reionization all require revision. Reionization may have begun earlier, proceeded more inhomogeneously, and been dominated by different source populations than current models assume. There is also a broader implication that connects JADES-GS-Z11 to the larger question of whether the Big Bang represents a true beginning. If galaxies sufficiently massive and ionizing luminous to clear 650,000 light-year bubbles around themselves existed only 330 million years after the purported beginning of time, then the causal chain from initial singularity to structured, massive, chemically enriched galaxy must have operated with extraordinary speed and efficiency. Every step in that chain, dark matter, halo formation, gas cooling and collapse, population 3 star formation and metal enrichment, galaxy assembly, black hole seeding and growth, would need to have been compressed into a time frame that strains the physics at every stage. The alternative, which Penrose and others have proposed, is that the initial conditions feeding this chain of events were not set at the Big Bang, but were inherited from a prior cosmic epoch. The Hubble tension crisis. The expansion rate of the universe is characterized by a single number known as the Hubble constant, denoted h0, which describes how rapidly the universe is expanding at the present epoch. Its units are kilometers per second per megaparsec, meaning that for every megaparsec of distance between two objects, where 1 megaparsec equals approximately 3.26 million light-years, those objects are receding from each other at a rate of h0 kilometers per second due to the expansion of space. This number is not merely a descriptive parameter. It sets the age of the universe, the distance to every cosmological object, the energy density required to produce a spatially flat universe, and the predicted abundances of light elements from Big Bang nucleosynthesis. It is, in a real sense, the most fundamental observable in cosmology. The problem is that two fundamentally different methods of measuring H0 consistently return values that disagree with each other at a level of statistical significance that has grown from a curiosity to a crisis over the past decade. The first method is based on the early universe. Using the precise measurements of the cosmic microwave background power spectrum obtained by the Planck satellite, cosmologists fit the Lambda CDM model to the data and extrapolate forward in time to predict the present-day expansion rate. The Planck 2018 analysis returned a value of 67.4 kilometers per second per megaparsec, with an uncertainty of 0.5 kilometers per second per megaparsec. This is a prediction derived from the physics of the early universe, and it is extraordinarily precise. The second method measures the expansion rate directly in the late universe using the cosmic distance ladder, a sequence of distance measurement techniques, each calibrated against the previous, that together span from nearby stars to cosmological distances. The lowest rung of this ladder uses parallax measurements of nearby Cepheid variable stars, stars whose luminosity oscillates with a period directly related to their intrinsic brightness. Once the period-luminosity relationship is calibrated, Cepheids can be used to measure distances to nearby galaxies containing them. Those galaxies, in turn, host Type 1a supernovae, which have standardizable peak luminosities and can be detected to much greater distances. By measuring the redshifts and distances of many Type 1a supernova, researchers can determine the expansion rate of the universe in the local volume. The primary team carrying out this measurement is the SH0ES collaboration, supernovae and H0 for the equation of state of dark energy, led by Adam Rees of Johns Hopkins University. The SH0ES value for H0, based on observations from both the Hubble Space Telescope and, crucially, the James Webb Space Telescope, has converged on approximately 73 kilometers per second per megaparsec, with an uncertainty of roughly 1 kilometer per second per megaparsec. The discrepancy between 67.4 and 73 is approximately 5 sigma, a level of statistical significance that in physics conventionally represents a discovery. The probability of this discrepancy arising from random measurement error alone, if the model is correct, is less than 1 in a million. The James Webb Space Telescope's contribution to this measurement was critical precisely because it could test one of the most persistent proposed explanations for the tension. That crowding and blending of Cepheid images in the dense stellar fields of host galaxies had systematically biased Hubble Space Telescope measurements of Cepheid brightnesses, and therefore distances, leading to an artificially elevated value of H0. Webb's superior angular resolution and infrared sensitivity allowed it to resolve Cepheids in the same host galaxies under conditions where stellar crowding was dramatically reduced. The results, published by Rees and colleagues in 2023, showed that crowding bias was not responsible for the discrepancy. Webb confirmed the SH0ES value of H0 with slightly reduced uncertainty, eliminating the most credible, mundane explanation for the tension. The tension is not confined to the Cepheid supernova distance ladder. Multiple independent late universe probes have returned values consistent with the SH0ES result. Measurements using the tip of the red giant branch, TRGB method, which uses the predictable luminosity of stars at the point where helium ignition terminates the red giant phase, have returned values between 69 and 72 kilometers per second per megaparsec, depending on the calibration sample used. Measurements using gravitational lensing time delays from the H0, LICO-W and TD Cosmo collaborations have returned values around 73 kilometers per second per megaparsec. Measurements using the angular diameter distances to baryon acoustic oscillation features in galaxy surveys, a technique that, like the CMB, is anchored in the early universe, return values closer to the Planck result, though the full dataset shows some tension depending on the survey. Measurements using the Tully-Fisher relation, linking galaxy rotation speed to luminosity, and surface brightness fluctuations in elliptical galaxies also tend toward higher values. The systematic coherence of the tension, the fact that late universe probes tend toward higher H0 values, while early universe probes tend toward lower values, is what elevates this from a measurement problem to a potential indicator of missing physics. If the discrepancy arose from unidentified systematic errors, one would expect the late universe measurements to scatter randomly around the Planck value, with some above and some below. Instead, they cluster consistently above it. This clustering suggests that either the Lambda CDM model's prediction of H0 from the early universe is wrong, meaning that the physics between recombination and the present epoch is not fully captured by the model, or that there is a fundamental difference in the physical character of the early and late universe that the model does not account for. Several theoretical proposals have been advanced to resolve the tension. Early dark energy models postulate a component of dark energy that was dynamically significant around the epoch of matter radiation equality, just before recombination, reducing the sound horizon scale and thereby shifting the Planck-inferred H0 upward. Interacting dark energy models allow dark energy to exchange energy with dark matter, modifying the expansion history. Modified gravity theories alter the relationship between matter density and expansion rate. Extra radiation species, such as additional neutrino flavors or other light particles, can similarly shift the early universe physics. None of these proposals has achieved consensus, in part because each tends to introduce new tensions with other cosmological observables when the relevant parameters are adjusted. The Hubble tension matters for the question of cosmic origins, not only because it signals missing physics in Lambda CDM, but because the specific nature of the discrepancy, the fact that the early and late universe appear to expand at systematically different rates, is precisely what would be expected if the initial conditions of the observable universe were not set by the Big Bang alone. In Penrose's conformal cyclic cosmology, as will be discussed in Part 2, the conditions inherited from a prior cosmic epoch could imprint subtle but measurable differences in the expansion history. In multiverse interaction scenarios, the merging or interaction of adjacent cosmic domains could alter the effective expansion rate in ways that mimic or produce the observed tension. These are not the only possible explanations, but the Hubble tension's persistent resistance to resolution within Lambda CDM has steadily widened the space of theoretical alternatives that must be taken seriously. The resistance of the tension to resolution through systematic effects deserves particular emphasis. The SH0ES team, over the course of a decade, has systematically eliminated one potential source of error after another. They have replaced photographic plates with CCD detectors, tested multiple period luminosity calibrations, used both optical and near-infrared Cepheid observations to reduce the effects of dust, and validated their Cepheid distances against alternative distance indicators, including the tip of the red giant branch, eclipsing binary stars, and water masses. Each refinement has left the H0 value essentially unchanged. The Webb confirmation in 2023, using the telescope's superior resolution to eliminate crowding bias at the level of individual Cepheid measurements, removed the most technically credible remaining escape route. On the other side of the ladder, the Planck collaboration has similarly cross-checked its CMB-derived H0 against independent probes of the early universe. The Atacama Cosmology Telescope, ACT, and the South Pole Telescope, SPT, have independently measured the CMB power spectrum and returned H0 values consistent with Planck. What this means is that the Hubble tension is not a problem that can be resolved by finding an error in either measurement. Both measurements appear to be correct within their stated uncertainties. The tension is a tension between two physically correct measurements of different things. The expansion rate of the late universe, measured directly, and the expansion rate of the late universe as predicted from the early universe under Lambda CDM, inferred from the CMB. If both measurements are right, then the model connecting them, Lambda CDM, must be wrong in some respect. The expansion history of the universe between recombination and the present must differ from what the model predicts. Something changed between then and now that the model does not capture. Whether that something is an early dark energy component, a modification of gravity on cosmological scales, a non-standard dark matter interaction, or evidence that the initial conditions of our universe were set not at the Big Bang, but at an earlier epoch. These possibilities are currently on roughly equal footing, constrained by the data, but not yet discriminated by it. What inflation cannot explain. Cosmic inflation, the hypothesis that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang, is not a single theory, but a family of models united by a common mechanism, a scalar field, generically called the inflaton, whose potential energy dominated the energy budget of the early universe, driving de Sitter-like expansion at rates far exceeding the speed of light. Inflation was proposed independently by Alan Guth in 1980 and Alexei Starobinsky in 1979, with Starobinsky's R-squared gravity model predating Guth's work, though Guth's paper framed the physical motivation more explicitly. The original motivation was not to explain the origin of structure, but to solve three problems that the pre-inflationary Big Bang model faced: the flatness problem, the horizon problem, and the monopole problem. The flatness problem concerns the spatial curvature of the universe. General relativity predicts that the energy density of the universe determines its geometry. If the density exceeds the critical value, approximately 9.47 times 10 to the power of minus 27 kilograms per cubic meter today, space is positively curved and finite. If it falls below, space is negatively curved and infinite. If it equals the critical density exactly, space is spatially flat. Observations, particularly from the Planck satellite, show that the universe is flat to within approximately 0.4%. Without inflation, achieving this degree of flatness requires the universe's initial density at the Planck time to have been fine-tuned to within 1 part in 10 to the power of 60 of the critical value. A fine-tuning that, without a dynamical mechanism to explain it, amounts to an unexplained initial condition. Inflation provides that mechanism. Any initial curvature is exponentially diluted during the inflationary expansion, driving the universe toward flatness, regardless of where it started. The horizon problem concerns the uniformity of the CMB. When we observe the microwave background, we find that its temperature is uniform to within approximately 1 part in 100,000 across the entire sky. In the standard Big Bang cosmology without inflation, regions of the CMB that are more than approximately 2 degrees apart on the sky were never in causal contact before the moment of last scattering. They were beyond each other's particle horizons. There is no physical mechanism in a non-inflationary model by which they could have equilibrated to the same temperature. Inflation resolves this by positing that what is now a vast, apparently causally disconnected region was before inflation a tiny volume well within the causal horizon. Inflation stretched a causally connected patch to cosmological scales. The monopole problem is related to the prediction, in many grand unified theories that topological defects including magnetic monopoles should have been produced copiously in the early universe at energy scales around 10 to the power of 15 giga-electron-volts. No magnetic monopoles have ever been detected. Inflation dilutes any relic monopoles to a density so low that they would be undetectable in the observable universe. Inflation's other major success, and arguably its most scientifically powerful prediction, is the production of a nearly scale-invariant spectrum of primordial density fluctuations. Quantum fluctuations in the inflaton field, stretched to macroscopic scales during inflation, produce density perturbations with an amplitude that varies very slowly with scale, characterized by a spectral index close to but slightly less than 1. The Planck measurement of the spectral index, 0.965, with an uncertainty of 0.004, is in excellent agreement with the predictions of the simplest inflationary models. Inflation also predicts a specific relationship between the amplitude of scalar, density, perturbations and tensor, gravitational wave, perturbations, characterized by the tensor to scalar ratio A/H(R), detection of primordial gravitational waves through their imprint on CMB polarization, specifically B-mode polarization, would represent the most direct confirmation of inflation. As of 2024, no confirmed detection of primordial B modes has been achieved. The most stringent upper limit on R is approximately 0.036 from combined BICEP/Keck and Planck data. Despite these successes, inflation confronts a set of deep theoretical problems that have resisted resolution for decades. The first is the initial conditions problem. Inflation requires that the inflaton field begin in a very specific configuration, near the top of its potential, with a sufficiently flat potential to sustain slow roll inflation for enough e-folds, a standard measure of inflationary expansion, with one e-fold corresponding to expansion by a factor of e, to solve the flatness and horizon problems. Typically, around 60 e-folds are required. The question of what set the inflaton in this configuration, what determined the initial state of the inflaton field, is not answered by inflation itself. It merely pushes the fine-tuning problem back one step, from the density of the universe to the configuration of the inflaton. The second problem is the measure problem in eternal inflation. In most inflationary models, inflation does not end everywhere simultaneously. Quantum fluctuations in the inflaton field cause inflation to end in some regions while continuing to drive exponential expansion in others. The regions where inflation ends become bubble universes, causally disconnected patches of space-time with their own physical properties. The inflating regions expand so rapidly that they always dominate the total volume, producing an infinite number of bubble universes, the multiverse of inflationary cosmology. This creates a severe problem for making predictions. In an infinite multiverse, every possible outcome occurs infinitely many times, and the probability of any specific observation becomes ill-defined without a measure, a way of weighting different outcomes. No consensus measure exists. The measure problem is not merely a technical difficulty, it threatens to render inflationary cosmology fundamentally unpredictive. The third problem is more directly relevant to the observations from Webb. Inflation does not by itself specify the efficiency of structure formation. It generates the primordial power spectrum, but the subsequent evolution of that spectrum into galaxies depends on the properties of dark matter, the dynamics of baryonic gas, and the feedback processes that regulate star formation. These are not determined by inflation. If the early universe contains galaxies more massive than the primordial power spectrum, combined with the best models of structure formation, can produce in the available time, which is precisely what Webb appears to show, then either the primordial power spectrum was different from what inflation, as constrained by Planck, predicts, or the structure formation physics is radically different from current models, or the initial conditions were not set by inflation at a single Big Bang event at all. A fourth and less frequently discussed limitation of inflation is its inability to address what came before. Inflation is presented as the mechanism that set the initial conditions for the hot Big Bang, but the inflaton field must itself have a prior history. Tracing the inflaton's evolution back in time leads inevitably to a regime of Planck-scale physics, energies above 10 to the power of 19 gigaelectron volts, where quantum gravitational effects dominate and general relativity is no longer applicable. In this regime, inflation's equations break down. The theory provides no description of the universe at or before the Planck time. It is silent on the question of origins in the most fundamental sense. It is a model of what happened after the initial moment, not of what caused or constituted that moment. For a theory widely presented as explaining the beginning of the universe, this is a significant limitation. And it is precisely the gap that conformal cyclic cosmology, among other cyclical cosmologies, attempts to fill. The inflationary paradigm also faces an observational challenge that is intensified with the non-detection of primordial gravitational waves. Many of the simplest and most theoretically motivated inflationary models, large field models such as phi-squared chaotic inflation and phi-fourth inflation, predict tensor-to-scalar ratios above 0.1. The upper limit from combined bicep/Keck array and Planck polarization data now sits at 0.036, ruling out these simple models entirely. The surviving inflationary models tend to be those with very flat potentials and very small field excursions, models that are less natural from a theoretical standpoint and that require additional fine-tuning of the inflaton potential. The inflationary model space has not been falsified, but it has been substantially constrained, and the surviving models are those that, ironically, are hardest to motivate from first principles. The implications of the eternal inflation framework deserve particular attention in this context. If inflation is eternal, if it continues indefinitely in regions where quantum fluctuations prevent the inflaton from rolling down its potential, then the multiverse is not a speculative add-on to inflationary cosmology, but an unavoidable prediction. In an eternal inflationary multiverse, the observable universe is one of an infinite number of bubble universes, each formed when inflation locally ended, each potentially with different physical constants, particle content, and dimensionality. This raises a profound question. If the multiverse is real, then what we observe as the initial conditions of our universe, the specific values of the cosmological parameters, the amplitude and spectral index of the primordial power spectrum, the ratio of baryons to dark matter, may be statistical accidents rather than fundamental laws. They may vary from bubble to bubble, and we happen to inhabit the bubble where they take values compatible with the existence of complex structure and observers. If this is the correct picture, then asking why the early universe produced the specific initial conditions that led to the structures Webb is now observing is, in principle, an unanswerable question within inflationary cosmology. The answer would simply be, because these are the conditions of our particular bubble, selected by the anthropic requirement that conditions be compatible with observers. This is not scientifically satisfying, and it is not scientifically testable in any conventional sense. Penrose has been particularly critical of this aspect of inflationary cosmology, arguing that it amounts to abandoning the scientific program of explaining the initial conditions of the universe. His alternative, conformal cyclic cosmology, attempts to derive the initial conditions of each new cosmic epoch from the physical properties of the one that preceded it, replacing anthropic selection with dynamical necessity. The first stars and the cosmic dark ages. Between the moment of recombination, when the universe became transparent to radiation at approximately 380,000 years after the Big Bang, and the ignition of the first stars, the universe passed through an era of profound darkness. This period, known as the Cosmic Dark Ages, lasted roughly 100 to 200 million years, depending on the model. During this time, the universe contained no luminous sources. The CMB photons, released at recombination, streamed freely through an increasingly transparent medium, cooling as they redshifted with the expansion. The matter content of the universe, baryons in the form of neutral hydrogen and helium, threaded by a sea of cold dark matter, was subject to gravity alone, slowly accreting into the filamentary web structure seeded by inflation's primordial perturbations. The dark matter component, being collisionless and cold, began forming gravitationally bound halos on small scales first, with these halos then merging hierarchically into progressively larger structures. Baryonic gas followed the gravitational potential wells of these halos, cooling through atomic and molecular hydrogen emission and collapsing toward the centers of the deepest potential wells. The first stars formed when the gas density within these halos became sufficient for gravitational collapse to overcome thermal pressure, a condition governed by the Jeans instability criterion, under which a cloud is unstable to collapse if its mass exceeds the Jeans mass, which is approximately proportional to the temperature to the power of 3/2 divided by the density to the power of 1/2. In the early universe, the absence of metals, elements heavier than helium, synthesized in stellar interiors and dispersed by supernovae, meant that gas cooling was far less efficient than in the present-day interstellar medium. Modern star formation relies heavily on metal line cooling and dust cooling to dissipate thermal energy, allowing gas clouds to fragment into the small, dense clumps that collapse into low-mass stars like the Sun. Without metals, the primary cooling mechanisms available to primordial gas were atomic hydrogen line emission, effective above about 8,000 Kelvin, and molecular hydrogen rho vibrational emission, effective at lower temperatures around 200 to 300 Kelvin, but easily destroyed by Lyman-Werner band ultraviolet photons. The consequence of inefficient cooling is that primordial gas clouds fragmented into much larger masses before collapsing, producing stars of characteristic mass perhaps 10 to 1,000 times the mass of the Sun, designated population 3 stars. Population 3 stars, if they existed in the mass range theorized, would have had surface temperatures above 100,000 Kelvin, luminosities millions of times that of the Sun, and lifetimes of only 1 to 3 million years before exploding as supernovae. Their intense ultraviolet radiation, both hydrogen ionizing photons shortward of 912 angstroms and Lyman-Werner photons in the 11.2 to 13.6 electron volts range, would have begun the process of reionizing and photodissociating the surrounding intergalactic medium almost immediately after their formation. Their supernovae would have dispersed the first heavy elements, carbon, oxygen, silicon, iron, into the surrounding gas, enriching it and enabling subsequent generations of stars to cool more efficiently and form with lower characteristic masses. The epoch at which population 3 stars first formed is poorly constrained by direct observation because these stars, being short-lived and existing at extreme redshifts, are extremely difficult to detect individually. The most optimistic estimates place the first population 3 stars at redshifts between 20 and 30, corresponding to between roughly 100 and 180 million years after the Big Bang. Webb's NIRCam and MIRI instruments have the sensitivity to potentially detect extremely bright individual population 3 stars through gravitational lensing, and several candidate lens population 3 stellar clusters have been proposed in early Webb data, though none has yet been definitively confirmed. The cosmic dark ages ended with the epoch of cosmic dawn, the term used to describe the period when the first luminous sources began transforming the universe. The 21-centimeter hydrogen line, produced by the hyperfine spin-flip transition of neutral hydrogen, is the primary observational probe of this era. During the cosmic dark ages, neutral hydrogen absorbs CMB photons at the 21 centimetre wavelength, redshifted to much longer wavelengths at the present epoch, producing an absorption feature in the radio spectrum. When the first stars form, their Lyman alpha radiation couples the spin temperature of hydrogen to the kinetic temperature of the gas, and their X-ray emission heats the gas above the CMB temperature, converting the 21 centimetre signal from absorption to emission. Ground-based radio telescopes, including the EDGES experiment and HERA, Hydrogen Epoch of Reionization Array, are attempting to detect this signal, with EDGES reporting a tentative detection of the 21 centimetre absorption trough in 2018 at a redshift of approximately 17, though this detection has been disputed on the grounds of potential systematic contamination. What is most relevant to the broader argument of this script is not the specific timing of population 3 star formation, but what the properties of these first stars imply about the efficiency with which the universe converted its initial conditions into organised, luminous structure. The Lambda CDM model predicts a relatively gradual build-up of stellar mass, with population 3 stars giving way to population 2 stars, metal-poor but not metal-free, which in turn seed the formation of the first galaxies over hundreds of millions of years. The objects Webb has detected, massive, structured, potentially metal-enriched galaxies existing when the universe was only 300 to 500 million years old, compress this entire sequence of events into a time frame that, even with optimistic assumptions about population 3 star formation beginning at redshift 25, leaves very little margin. If the first stars formed at redshift 25, roughly 130 million years after the Big Bang, and the most massive Webb-detected galaxies were already fully assembled at redshift 12, roughly 370 million years after the Big Bang, then the entire process of metal enrichment, feedback regulation, galaxy assembly, and stellar mass accumulation compressed into approximately 240 million years. For context, the Milky Way, with its 250 billion solar masses of stars, has been forming stars for approximately 13 billion years. The claim that comparable or larger stellar masses assembled in less than 2% of that time, from an initially pristine, metal-free medium, requires either that the physics of early star formation was categorically different from what we model, or that the initial conditions were not those of a standard Big Bang. Both possibilities demand investigation at the level of fundamental physics. The cosmic dark ages, in this sense, are not merely a quiet prologue to the drama of structure formation. They are a boundary condition, a testable constraint on what could have existed before the first light. If the universe that emerged from the Big Bang was as simple, as uniform, and as devoid of structure as the CMB appears to show, then what came after it had to have been produced entirely by the physics of that simple initial state. Webb's observations increasingly suggest that the simple initial state was not simple enough, that the universe was, in some sense, already richer in organised structure than a smooth, isotropic, 13.8 billion-year-old cosmos beginning from nothing should have been able to produce in the time available. That inference, if sustained by continued observation, points toward the possibility that the Big Bang was not a beginning from nothing but a transition from something that came before. The population 3 star problem crystallizes this tension most sharply. The standard model requires that population 3 stars, the first generation, formed from metal-free gas, were the progenitors of all subsequent stellar populations, providing the first metals and establishing the conditions for normal galaxy formation. Their lifetimes of 1 to 3 million years set a minimum clock for the enrichment process. If the first population 3 stars formed at redshift 25, then by redshift 20 they were already dead, having dispersed their metals. But these metals then need to be mixed into the surrounding interstellar and circumgalactic medium, cool further, and seed the formation of second-generation population 2 stars, a process that itself takes tens to hundreds of millions of years in standard models. The galaxies Webb sees at redshift 12, already containing what appear to be mature multi-generation stellar populations with measurable metallicities, have compressed this entire sequence into a timeline that may be physically impossible under standard stellar evolution and chemical enrichment models. Researchers, including Anna de Graaf of the Max Planck Institute for Astronomy and Luca Constantin of the Spanish National Research Council, have, in separate studies using Webb NER-SPEC data from 2023 and 2024, identified what appear to be massive quiescent galaxies, galaxies that have already shut down their star formation, at redshifts between 4 and 5, corresponding to when the universe was only 1.2 to 1.5 billion years old. For a galaxy to have formed stars rapidly enough to build up billions of solar masses of stellar material, then stop forming stars, all within the first 1 to 1.5 billion years of cosmic history, requires star formation efficiencies and quenching timescales that are incompatible with the predictions of virtually every current galaxy formation model calibrated to lower redshift observations. What the cosmic dark ages represent, therefore, is not merely an observational gap in our data, a period we cannot directly see because no light escaped it, but a theoretical choke point. Every galaxy Webb observes at high redshift had to pass through the dark ages on its way to existence. Whatever physical processes produced, the universe breakers had to operate during or immediately after that dark era. If those processes were entirely consistent with the standard model of a universe born 13.8 billion years ago from a hot, smooth Big Bang, then we should not be seeing what Webb is seeing. The systematic and coherent nature of the tension, spanning galaxy masses, reionization history, the Hubble constant, and the matter-power spectrum suggests that the dark ages were not simply a quiet waiting period between the Big Bang and the first stars. They may have been an era in which the universe was already far more structured, far more active, and far more informed by prior cosmic history than the standard model assumes is possible. Penrose and conformal cyclic cosmology. Roger Penrose is not a cosmologist by primary training. He is a mathematician and mathematical physicist whose contributions to general relativity, quantum mechanics, and the foundations of space-time geometry span more than 6 decades. He shared the 2020 Nobel Prize in Physics with Reinhard Genzel and Andrea Ghez for the proof that black hole formation is a robust prediction of general relativity, a result he derived in 1965 in collaboration with Stephen Hawking, building on Hawking's earlier singularity theorems. His work on the Penrose process, energy extraction from rotating black holes, twistor theory, spin networks, and the geometry of space-time has shaped modern theoretical physics in ways that extend far beyond any single discovery. When Penrose proposes a cosmological theory, it is not the product of speculative enthusiasm. It is the product of decades of engagement with the mathematical structure of general relativity and quantum field theory at their deepest levels. Conformal cyclic cosmology, which Penrose introduced in lectures and papers beginning around 2005 and developed at length in his 2010 book Cycles of Time, rests on a mathematical observation about the structure of space-time at the 2 temporal extremes of a universe's history, its beginning and its end. The key concept is conformal geometry, a branch of differential geometry concerned with the angles between curves rather than the absolute distances between points. A conformal transformation rescales distances at every point in space by a spatially varying factor, preserving angles and local shapes but altering sizes. 2 spacetimes are conformally equivalent if one can be obtained from the other by such a rescaling. Penrose's central observation is that the Big Bang, the initial singularity of our universe, and the far future of our universe, the asymptotically de sitter space, produced by the dominance of dark energy as all matter eventually disperses or decays, share a deep mathematical property. Both are conformally smooth, even though they are physically singular in the case of the Big Bang, or infinitely expanded in the case of the far future. In the standard representation of space-time using Penrose diagrams, both the initial and final boundaries of a universe dominated by a positive cosmological constant are space-like hypersurfaces, extended regions of space-time, not points, and both admit a well-defined conformal structure. The critical physical argument that drives CCC concerns what happens to the matter content of the universe in the very far future. In a universe dominated by dark energy, the expansion accelerates exponentially, and matter becomes increasingly dilute. Penrose argues that in the ultimate fate of such a universe, after a timescale vastly longer than the current age of the universe, on the order of 10 to the power of 100 years or more, all massive particles will have either fallen into black holes, been evaporated as Hawking radiation, or decayed into massless particles such as photons and gravitons. The last surviving massive particles in this scenario are protons, and even these, if proton decay occurs, as predicted by grand unified theories, with a lifetime above 10 to the power of 34 years, will eventually decay. In a universe containing only massless particles, something remarkable happens mathematically. The concept of rest mass vanishes, and with it, the concept of a fixed time interval defined by the rest mass oscillation frequency of particles. Massless particles travel at the speed of light by definition and experience no proper time. The space-time interval along a null geodesic is zero. In a universe populated entirely by massless particles, there is no intrinsic scale by which to measure time or distance. Such a universe is therefore conformally equivalent to one that has no scale, one that could, in principle, be conformally rescaled to look like the Big Bang singularity of a new universe. This is the mathematical heart of CCC. The conformally smooth remote future of one cosmic aeon is identified via a conformal rescaling, with the conformally smooth Big Bang of the next. The two boundaries are matched. The remote future of one universe becomes the initial singularity of the next, in what Penrose calls a conformal cyclic transition or crossover. This is not a physical recycling in the sense of matter or energy being carried forward in any conventional sense. The conformal rescaling is a mathematical identification of the geometric structure of two different spacetimes. What is preserved across the crossover is not material content, but geometric information, specifically the structure of gravitational degrees of freedom encoded in the Weyl curvature tensor. The Weyl tensor characterizes the tidal and shear components of space-time curvature, the components not determined by the local matter distribution, which is described by the Ricci tensor and, through the Einstein equations, by the stress-energy tensor. At the Big Bang, Penrose argues, the Weyl curvature must have been extraordinarily small, close to zero, as evidenced by the high degree of homogeneity and isotropy of the CMB. This is the Weyl curvature hypothesis, that the initial singularity is characterized by vanishing Weyl curvature, a condition that is not predicted by inflation, and whose explanation within inflationary cosmology requires fine-tuning. In CCC, the vanishing Weyl curvature at each new Big Bang is explained dynamically. It is a consequence of the conformal smoothness of the preceding aeon's remote future. The low entropy, low Weyl curvature initial conditions of each new cosmic epoch are not a fine-tuned coincidence. They are imposed by the mathematical structure of the transition. Each aeon begins in a state of low gravitational entropy, smooth, uncurved spacetime, and high thermodynamic entropy potential, allowing the second law of thermodynamics to operate and structure to form. This is Penrose's solution to the deep problem of why our universe began in a state of such extraordinarily low entropy, a problem that statistical mechanics regards as the most improbable of initial conditions. In CCC, the low entropy of the Big Bang is not improbable. It is inevitable, imposed by the geometry of the preceding aeon. The implications of this framework for the JWST observations are indirect but significant. If the initial conditions of our universe were not randomly drawn from some prior free distribution, but were shaped by the geometry of a preceding cosmic epoch, then those initial conditions could carry information, subtle imprints of the prior aeon structure, that might manifest as deviations from the predictions of a universe starting from pure inflation. The structures Webb observes, galaxies more massive, more organized, and more chemically enriched than the standard model predicts, could, in principle, reflect initial conditions that were not purely random quantum fluctuations, but were structured by the conformal geometry of the previous aeon. Penrose has not claimed this connection explicitly, but it is a natural implication of the framework. CCC also has something to say about the second law of thermodynamics and the arrow of time, questions that are intimately connected to the problem of initial conditions. The arrow of time, the observable directionality of physical processes from organized to disorganized states, is a consequence of the second law of thermodynamics, which states that the entropy of a closed system does not decrease. But the second law does not follow from the microscopic laws of physics, which are time-symmetric. The fundamental equations of both classical mechanics and quantum mechanics are invariant under time reversal. The second law is therefore a statement about initial conditions, not about dynamics. It holds in our universe because the universe began in a state of extraordinarily low entropy, a state of high organization and low disorder, and has been evolving toward higher entropy ever since. The question of why the universe began in such a low entropy state is, in a very real sense, the deepest question in physics. Standard inflationary cosmology does not answer this question. It explains why the universe was spatially flat and thermally uniform at the time of the Big Bang. But spatial flatness and thermal uniformity are not the same as low entropy. The gravitational degrees of freedom, the Weyl curvature, were also in a state of extraordinary low entropy at the Big Bang, as evidenced by the fact that the initial singularity was smooth and uncurved, rather than chaotic and highly curved. Inflation does not explain this gravitational low entropy initial condition. It assumes it. Penrose's Weyl curvature hypothesis, the proposal that the initial singularity is characterized by vanishing Weyl curvature, is his candidate for the correct statement of the low entropy initial condition. It is a geometric condition. The initial singularity must be conformally smooth, meaning that the tidal and shear distortions of space-time geometry must be zero or negligible at the Big Bang, even though the Ricci curvature, determined by the matter density, diverges. This is an extremely special condition. Almost all possible initial singularities in general relativity are highly chaotic, with wildly varying Weyl curvature, what Penrose calls the BKL oscillations, after Belinsky, Kalatnikov, and Lifshitz, who characterized the generic behavior of general relativistic singularities in the late 1960s. A smooth, Weyl zero initial singularity is a set of measure zero in the space of all possible initial conditions for a singularity. It is, in statistical terms, infinitely improbable relative to a randomly chosen initial state. In CCC, the Weyl curvature hypothesis is not a postulate that requires separate justification. It is a theorem. The conformal geometry of the preceding aeon's remote future automatically produces a conformally smooth initial singularity for the new aeon. The smoothness is inherited from the smoothness of the conformal boundary at the end of the previous aeon. This is the most profound feature of CCC as a physical theory. It converts the most baffling fine-tuning in cosmology, the initial entropy of the universe, from an unexplained given into a derived consequence of the cyclic geometry. If CCC is correct, the arrow of time in our universe is not an accident or an anthropic selection. It is a mathematical necessity imposed by the physics of the previous aeon's conclusion. The geometry of eternity. The mathematical machinery underlying conformal cyclic cosmology is rooted in a specific representation of spacetime known as conformal compactification, a technique developed by Penrose himself in the 1960s as a tool for studying the global structure of spacetime and the propagation of light signals over cosmological distances. In conformal compactification, the infinite extent of spacetime is mapped to a finite diagram, the Penrose diagram, by applying a conformal transformation that brings the boundaries of spacetime, past and future infinity, spatial infinity, to finite locations in the diagram. This mapping preserves the causal structure of spacetime, which events can influence which other events, while compressing the infinite extent into a finite picture. In the Penrose diagram of a day-sitter universe, the spacetime geometry produced by a positive cosmological constant, the future boundary is a space-like surface known as future conformal infinity, denoted in the mathematical literature as scree plus, written as a script I with a plus superscript. This surface represents the endpoint of all future directed null geodesics, light rays, in the spacetime. In a de-sitter universe, this surface is smooth and geometrically well-behaved. It has finite curvature, a well-defined metric up to conformal rescaling, and no singularity structure. Penrose's insight is that this smooth future boundary of one universe can be conformally identified with the smooth past boundary, the Big Bang, of the next, because both boundaries have the same conformal structure in the limit, where all massive fields have died away. The technical requirement for this identification to work is precisely the condition Penrose discusses regarding massless particles. In a universe where all massive particles have decayed, the stress-energy tensor at late times is dominated by radiation, massless fields, and the conformal factor that relates the physical metric to the conformally rescaled metric approaches zero as the future boundary is approached. This vanishing conformal factor is what allows the remote future to be smoothly connected via conformal rescaling to the Big Bang of the next aeon. The transition is not physically observable from within any single aeon. No observer within our universe can receive signals from the previous aeon or send signals to the next, because the conformal boundary acts as an absolute causal horizon. The information that crosses the boundary is encoded in the geometric structure of the gravitational field, not in the quantum states of individual particles. This raises an immediate question about entropy. The second law of thermodynamics states that entropy is non-decreasing in any closed system. If a universe begins in a low entropy state and ends in a high entropy state, as ours evidently will, given that the ultimate fate of our universe is a cold, dark, maximally expanded state containing only dilute radiation and the fading remnants of evaporated black holes, then how can the next universe begin in a low entropy state? Doesn't CCC violate the second law? Penrose's answer involves a careful distinction between two types of entropy: the thermodynamic entropy of matter and radiation, which is high at the far future of an eon, and the gravitational entropy encoded in the Weyl curvature, which is low at the far future of an aeon, because the intense gravitational inhomogeneity created by black holes disappears when those black holes evaporate via Hawking radiation, leaving a smooth spacetime. The second law governs the total entropy, but the total entropy in Penrose's framework must include both contributions. At the Big Bang of a new aeon, the thermodynamic entropy is effectively reset. The matter content of the new ion is born from the conformal structure of the preceding ion's geometry, not from its high entropy radiation, while the gravitational entropy starts from zero because the space-time curvature at the new Big Bang is conformally constrained to be smooth. The net result is that each new ion begins in a state of low total entropy, consistent with the second law operating within each ion without contradiction. This is not a trivial claim. It requires that the conformal matching at the crossover genuinely produces a thermodynamic reset, that the high entropy radiation of the old aeon does not carry its entropy into the new one in a way that violates the thermodynamic initial conditions. Penrose argues that the conformal rescaling effectively changes the physical interpretation of energy and entropy. What counts as high entropy in the old aeon, dilute, uniform radiation, corresponds after the conformal rescaling to low gravitational entropy in the new ion, a smooth, uncurved initial singularity. The two entropy bookkeeping systems are incommensurable across the crossover because the definition of scale, and therefore the definition of entropy density, changes discontinuously at the conformal transition. The geometry of eternity in CCC is therefore not a simple cycle in which the universe returns to the same state. It is an infinite sequence of aeons, each beginning with low gravitational entropy and ending with high thermodynamic entropy, connected by conformal transitions that reset the gravitational geometry while preserving certain information in the form of the Weyl curvature structure. Each ion is causally isolated from the others in the conventional sense. No particle or signal can cross from one ion to the next. But the gravitational geometry of each new ion carries the imprint of the physics of the previous ion's late-time structure. This imprint is subtle and would manifest not as macroscopic features visible to observers within the new ion, but as specific statistical patterns in the cosmic microwave background, patterns of the type that Penrose and collaborators claim to have detected, and that are discussed in detail in the following chapter. The conceptual elegance of CCC lies in its economy. It does not require new fundamental forces, new particles, or modifications to general relativity. It requires only that the asymptotic future of a universe dominated by a positive cosmological constant, precisely the kind of universe we inhabit, has a conformal structure that can be matched to the Big Bang of a successor universe. The cosmological constant, which in Lambda CDM is a mysterious parameter with no theoretical explanation, plays a central and necessary role in CCC. It ensures that the universe's future is de Sitter-like, with a smooth, conformal boundary that enables the cyclic transition. In this sense, the cosmological constant is not an unexplained parameter in CCC, but a structural requirement. The universe must accelerate in its late stages in order to produce the conformally smooth future boundary that the cyclic transition demands. Chapter 9. Hawking Points in the CMB. The observational cornerstone of conformal cyclic cosmology is the prediction of specific anomalies in the cosmic microwave background that have no explanation within standard inflationary cosmology. These anomalies arise from a physical process that operates during the late stages of the preceding aeon, the evaporation of supermassive black holes via Hawking radiation, and leave imprints in the conformal geometry that are transmitted to the CMB of the new aeon. Stephen Hawking demonstrated in 1974 that black holes are not perfectly black, but emit thermal radiation at a temperature inversely proportional to their mass. Specifically, a temperature of approximately 6.17 times 10 to the power of -8 solar masses divided by the black hole mass in Kelvin. For a stellar mass black hole of 10 solar masses, this temperature is approximately 6 times 10 to the power of -9 Kelvin, far below the present CMB temperature of 2.725 Kelvin, meaning that stellar mass black holes absorb CMB photons more rapidly than they emit Hawking radiation and grow rather than shrink in the current epoch. But in the far future of the universe, after the CMB has redshifted to negligibly low temperatures, as the universe expands by many orders of magnitude, even supermassive black holes will begin to lose mass through Hawking radiation faster than they absorb radiation from their environment. The evaporation timescale for a black hole of mass m in solar masses scales as m cubed. Specifically, the evaporation time is approximately 2.1 times 10 to the power of 67 years, times the cube of the mass in solar masses. For a supermassive black hole of 10 billion solar masses, comparable to the largest known black holes, such as TON 618 at 66 billion solar masses, or the black hole at the centre of the galaxy. Holm 15A at approximately 40 billion solar masses. The evaporation time is on the order of 10 to the power of 97 years. This is vastly longer than the current age of the universe, 13.8 billion years, but finite. In the remote future of the aeon preceding ours, if CCC is correct, supermassive black holes were the last surviving massive objects, slowly evaporating over timescales that dwarf anything in the observable universe's current history. As each supermassive black hole evaporates, the energy it has accumulated over billions of years, the rest mass energy of all the stars, gas, and smaller black holes that fell into it, plus the gravitational energy released during those accretion events, is ultimately radiated away as Hawking radiation. This radiation emerges in a spherical shell expanding outward from the black hole's location at the speed of light. As the evaporation nears completion, the temperature of the Hawking radiation rises, because temperature is inversely proportional to mass, and the black hole is losing mass, producing a final burst of high-energy emission. The energy deposited in the universe by this evaporation is not distributed randomly. It is concentrated in a spherical region centered on the black hole's location, with an intensity profile that falls off as the inverse square of the angular distance from the center. In CCC, this spherical concentration of energy from a black hole evaporation in the preceding aeon creates a local enhancement in the conformal geometry at the crossover. This enhancement is transmitted to the CMB of the new ion as a disc-shaped region of slightly elevated temperature, a hotspot with a roughly circular boundary. Penrose and colleagues calculated the expected angular size of these features, given the typical masses and final evaporation energies of supermassive black holes in the preceding aeon. The features should appear as disks with angular diameters on the order of 1 to several degrees on the sky, comparable to the apparent size of the full moon, which subtends approximately 0.5 degrees. Because the temperature enhancement is created by the spherical symmetry of the Hawking radiation burst, the features should appear as nearly perfect circles in the CMB temperature map, distinct from the irregular, non-circular temperature fluctuations produced by acoustic oscillations in the standard inflationary model. Penrose, working with Vahe Gurzadyan of the Yerevan Physics Institute, reported in 2010 the detection of circular patterns in the CMB data from the WMAP, Wilkinson Microwave Anisotropy Probe, satellite that were consistent with this prediction. Their analysis, published in a paper available on the Arcueif preprint server, identified concentric rings in the CMB temperature map, along which the variance, the statistical spread of temperature values, was anomalously low compared to the surrounding sky. This is the signature expected from a Hawking point. The conformal imprint of a black hole evaporation would produce a region of reduced temperature variance, a quiet disk, superimposed on the stochastic temperature fluctuations of the inflationary power spectrum. In 2018, Penrose and colleagues published a follow-up analysis using data from the Planck satellite, which provided higher angular resolution and lower noise than WMAP, and reported not only the confirmation of the low variance circular features identified in the WMAP data, but the identification of a specific subset of features that match the predicted properties of Hawking points more precisely. This analysis, co-authored with Daniel Ahn of the State University of New York and Krzysztof Meissner of the University of Warsaw, claimed to identify approximately 20 candidate Hawking points in the Planck CMB data, with angular diameters consistent with the predicted range and with statistical significance. They estimated it between 3 and 4 sigma, above the null hypothesis of a purely inflationary CMB. The specific features identified were not merely hotspots, but had a more complex structure. Penrose and colleagues described them as exhibiting a bright central disk surrounded by a ring of slightly reduced temperature, a profile consistent with the theoretical expectation for the Hawking radiation burst from a single supermassive black hole evaporation, which would produce a central concentration of energy surrounded by a slightly depleted region from which radiation had been drawn toward the evaporating black hole during the late stages of evaporation. The angular positions of the candidate Hawking points on the sky showed no obvious clustering with known foreground structures, suggesting they were not artifacts of galactic contamination. The Planck data also enabled a more precise test of a secondary prediction of CCC, that Hawking points should appear above the otherwise random distribution of CMB hotspots in a statistically characterizable way. Specifically, in a purely inflationary CMB, the distribution of hotspots above a given temperature threshold should follow a specific statistical distribution determined by the power spectrum. Hawking points, being deterministic imprints of specific physical events in the prior aeon, rather than random fluctuations, should produce an excess of circularly symmetric hotspots above the inflationary expectation at the angular scales corresponding to their predicted size. The Penrose team's analysis of the Planck data reported such an excess, with a statistical significance that, while not reaching the 5 sigma threshold conventionally required for a discovery claim, was sufficient to constitute a meaningful observational test of the theory. Whether these features constitute genuine evidence for CCC or statistical artifacts of the CMB analysis is a question that has generated substantial debate in the literature, which the following chapter addresses in detail. What is not in dispute is that the Hawking point prediction is a genuine, quantitative, and potentially falsifiable prediction of CCC, one that can be tested with existing CMB data and with future data from experiments including the Simons Observatory and CMBS-4. This is what distinguishes CCC from many other speculative cosmological theories. It makes specific predictions about observable features in the CMB that would not be expected in any inflationary model. The skeptics and the evidence. The scientific response to Penrose and Ghazardian's 2010 claim of circular anomalies in the CMB was swift and skeptical. Within months, 3 independent groups, including teams led by Ingunn Weihus and Hans Christian Eriksson at the University of Oslo, Adam Moss, Douglas Scott, and James Zibin at the University of British Columbia, and Amir Hajian at Princeton University, published analyses using the same WMAP dataset that Penrose and Ghazardian had used, and reported that they could find no statistically significant excess of circular low variance features beyond what was expected from a standard inflationary CMB. Their conclusion was that the features identified by Penrose and Ghazardian were consistent with random fluctuations in the inflationary power spectrum, that if you look hard enough at a noisy dataset, circular patterns will emerge by chance, and the appropriate statistical test is to compare the observed frequency and significance of such patterns against simulated CMB maps generated from the standard model. The core of the methodological dispute is subtle but important. Penrose and Gozardian argued that the circular features they identified were anomalously low in variance. That is, the temperature fluctuations within the rings were suppressed relative to the average CMB. The critics argued that the specific statistical test used to quantify this suppression was not properly calibrated against the null hypothesis of a Gaussian inflationary CMB, that the simulations used to establish the expected variance distribution did not adequately account for all sources of non-Gaussianity and anisotropy in the WMAP data, including instrument noise, foreground contamination, and the effects of the data processing pipeline. When the simulations were corrected for these effects, the critics found the observed features were no longer anomalous. Penrose and colleagues contested this response on multiple grounds. They argued that the critics had used different definitions of the circular features, different radii, different thresholds, different methods of identifying candidate circles, and that these differences in implementation were responsible for the discrepancy in results. They also argued that the 2018 Planck-based analysis, which used superior data and a different and more theoretically motivated set of predictions, was not addressed by the original WMAP-era critiques. The Planck analysis introduced the concept of Hawking points as a specific theoretical prediction, not merely a search for any circular low-variance features, but a prediction of features with specific angular sizes, specific temperature profiles, hot center, slightly cool surroundings, and a specific expected number density, and argued that this theoretically motivated search was less susceptible to the look elsewhere effect that plagued the more general circle search. The look elsewhere effect is a fundamental issue in the statistics of pattern recognition in complex datasets. When searching for anomalous features in a dataset without a specific prior prediction of where they should appear, the appropriate statistical significance threshold must be corrected for the number of possible feature locations, scales, and morphologies that were implicitly searched. A feature that appears significant in isolation may be unremarkable when the full parameter space of the search is accounted for. The Planck collaboration's own analysis of the CMB data found no statistically significant evidence for features inconsistent with the inflationary Lambda CDM model, though the collaboration searches were not specifically designed to detect the CCC Hawking point signature. What the skeptical literature makes clear is that the current status of the Hawking point evidence is contested but not definitively refuted. The key observational tests that would sharpen this situation have not yet been performed. The Simons Observatory, currently under construction in the Atacama Desert in Chile, will measure the CMB polarization and temperature anisotropies at angular resolutions and sensitivities substantially beyond those of Planck. An angular resolution of approximately 1 arc-minute at 90 GHz and a noise level of approximately 6 microkelvin arc-minutes. CMBS-4, a next-generation ground-based experiment funded by the US Department of Energy and National Science Foundation, is designed to achieve noise levels of approximately 1 microkelvin arc-minute over a large sky fraction, representing a factor of several tens improvement over Planck in sensitivity. These experiments will provide data of sufficient quality to test the Hawking point prediction at the level of statistical significance required to either confirm or rule it out definitively. In assessing the evidence, it is important to distinguish between two separate claims. The first is the statistical claim that the existing CMB data contains circular features at a frequency and significance level that cannot be explained by the standard inflationary model. The second is the theoretical claim that CCC provides the correct physical explanation for these features should they be confirmed. These claims are logically independent. The first can, in principle, be resolved by improved data analysis and better calibrated simulations. The second requires both confirmation of the features and elimination of alternative explanations. Penrose himself has consistently presented the Hawking point evidence as strongly suggestive rather than conclusive, and has acknowledged that the statistical case will need to be strengthened by future observations to achieve scientific consensus. It is also worth noting that the standard inflationary model itself faces observational anomalies in the CMB that the model does not predict. These include the CMB quadrupole anomaly, the fact that the quadrupole moment of the CMB power spectrum, the largest scale temperature pattern, is anomalously low by approximately a factor of 7 relative to the best fit Lambda CDM model. The alignment of the low multipole moments of the CMB, the so-called axis of evil, and several large-scale cold spots, most notably the CMB cold spot in the southern sky, which subtends approximately 10 degrees and appears to have a temperature about 70 microkelvin below the mean. These anomalies, while individually within the range of random fluctuations at the 2 to 3 sigma level, form a pattern of large-scale departures from statistical isotropy that is not predicted by inflation. Whether these features are related to the Hawking point signature or represent independent evidence for physics beyond Lambda CDM is an open question that improved CMB data from the Simons Observatory and CMB-S4 will directly test. The statistical methodology debate has deeper roots that extend beyond the specific case of Hawking points. The CMB is a single realization of a stochastic process, and the analysis of such a dataset for anomalous features requires careful attention to the distinction between features identified before and after examining the data. If a researcher examines a dataset and identifies a pattern, then constructs a statistical test for that specific pattern, the significance of the test result is inflated by the fact that the pattern was chosen post hoc. The appropriate correction for this, the look elsewhere effect, requires knowing the full space of patterns that were implicitly searched before the reported feature was selected. For circularly symmetric features in the CMB, the relevant parameter space includes all possible center locations on the sky, all possible radii, all possible amplitude thresholds, and all possible morphological variants. The correction factor can be enormous, potentially reducing an apparently significant detection to a marginal one. Penrose and colleagues have argued that their 2018 Planck-based search was less susceptible to the look elsewhere problem than the original 2010 WMAP circle search, because the Hawking point prediction specifies a relatively narrow range of angular sizes based on the predicted masses of evaporating supermassive black holes, and a specific temperature profile, hot center, slightly cool surroundings, that reduces the effective search parameter space. This argument has merit in principle, though it requires that the theoretical predictions be sufficiently precise to genuinely constrain the search space. The theoretical uncertainty in the predicted Hawking point angular size is itself substantial. It depends on the distribution of supermassive black hole masses in the preceding aeon, which is unknown. A range of angular sizes spanning a factor of several still corresponds to a large search parameter space. The resolution of this debate ultimately lies not in the analysis of existing data, but in the acquisition of new data. The Simons Observatory's combination of large aperture telescope, 6-meter primary mirror, and small aperture telescopes will measure the CMB temperature and polarization power spectra at angular resolutions and sensitivities that substantially exceed Planck across the multipole range from 2 to approximately 10,000. Critically, the polarization data will provide an independent test of any temperature-based anomaly. A genuine physical feature, whether a Hawking point or any other pre-inflationary imprint, should appear in both temperature and polarization maps in a specific correlated way determined by the physics of Thomson's scattering at last scattering. A feature that appears only in temperature and not in the correlated polarization pattern would be inconsistent with a physical origin and more likely to be a noise artifact or a foreground contamination. If the Hawking point candidates survive scrutiny in the Simons Observatory data and appear consistently in both temperature and polarization. With the correct morphological relationship, the statistical case will become substantially more compelling. Multiverse interactions and expansion. The Hubble tension and the anomalous properties of high redshift galaxies have, independently of the CCC framework, motivated a class of theoretical proposals involving interactions between our universe and adjacent cosmic domains. These proposals are distinct from the eternal inflation multiverse, where bubble universes are causally disconnected after their formation, and from CCC, which involves sequential rather than parallel universes. They represent a third class of non-standard cosmology, one in which the observable universe is embedded in a larger structure with which it has exchanged energy, momentum, or information in a way that has left measurable imprints on its physical properties. The motivation for considering such interactions begins with a specific feature of the Hubble tension: the fact that the discrepancy between the early universe and late universe measurements of the expansion rate has a specific magnitude, approximately 8 to 9% between the Planck value of 67.4 and the SH0 value of approximately 73 kilometers per second per megaparsec, and a specific sign: the late universe always expands faster than the early universe prediction, never slower. This directionality is what distinguishes the Hubble tension from a random measurement error and suggests a systematic physical cause. One class of physical causes that produces a directional modification of the expansion rate is a bulk flow, a coherent motion of the observable universe relative to some larger reference frame, superimposed on the cosmological expansion. If the observable universe is moving through a larger structure, the apparent expansion rate measured from within it would be anisotropic, appearing different in different directions. Current measurements do not show strong evidence for the level of anisotropy required by a simple bulk flow explanation, but more complex geometries are not excluded. A more theoretically developed proposal involves what has been called cosmological bubble nucleation, a scenario in which the early inflationary phase of our universe was not an isolated event, but occurred within a pre-existing metastable vacuum state, with the nucleation of our bubble universe being triggered or influenced by nearby nucleation events in adjacent regions of a broader inflationary sea. If two bubble universes nucleated sufficiently close together in the inflationary sea, they could have interacted during or shortly after their formation, exchanging energy through a brief period of causal contact before their mutual recession, driven by the expansion of the intervening inflationary space, cut them off from each other. The energy deposited in our universe by such a collision would have been distributed non-uniformly on the sky and would have left a specific imprint in the CMB, a disc-shaped region with anomalous temperature and polarization patterns at the location of the collision. Researchers, including Matthew Johnson of the Perimeter Institute and Luis Lehner of the Perimeter Institute and Hiranya Peiris of University College London, have developed detailed predictions for the CMB signatures of bubble universe collisions and compared them against Planck data. Their searches have not produced a confirmed detection, and their upper limits constrain the energy deposited by any hypothetical collision to below the level that could resolve the Hubble tension on its own. However, more recent proposals have extended the interaction framework beyond simple bubble collisions. A class of models developed by researchers at several institutions in 2023 and 2024 proposes that the apparent expansion rate of our universe could be modified if our universe is embedded in a larger scale structure, what these authors call a parent universe, whose gravitational influence has persisted into our current epoch. In this scenario, the inflationary expansion of our universe did not occur in isolation, but within a pre-existing gravitational potential well created by the parent structure. The effective dark energy density in our universe, which drives the current accelerating expansion and is parameterized by the cosmological constant lambda, would receive a contribution from this embedding, an additional term in the Friedmann equations that modifies the expansion history in a way that could shift the predicted H0 from the Planck value toward the SH0 ES value. When researchers calibrated these models to the Planck CMB data and the DESIBAO measurements while allowing the embedding term to vary as a free parameter, they found that values of this term consistent with resolving the Hubble tension did not violate the CMB or BAO constraints. This is a non-trivial result. It means that a universe embedded in a larger structure is not ruled out by any currently available cosmological dataset, and that the embedding could, in principle, simultaneously explain the Hubble tension and alter the initial conditions of structure formation in a way that might address the high redshift galaxy mass problem. The mechanism is not merely adding a constant. It modifies the time evolution of the expansion rate in a specific way that depends on the geometry and density of the parent structure. The connection between these multiverse interaction models and the JWST observations becomes particularly interesting when considering the initial power spectrum. In standard inflation, the primordial power spectrum is nearly scale invariant with a slight red tilt, more power on large scales than small scales, as measured by Planck. But if the inflationary phase of our universe occurred within a larger structure that had its own density fluctuations and gravitational influence, the effective primordial power spectrum in our universe would be modified, potentially enhanced on scales corresponding to the density structure of the parent universe. An enhanced primordial power spectrum on the scales corresponding to the first galaxies, co-moving scales of roughly 0.1 to 10 megaparsecs, would produce more dark matter halos at early times, enabling more rapid and efficient galaxy formation, and could naturally explain the excess of massive high redshift galaxies that Webb has detected. This is a speculative but quantitatively testable proposal. The DESIBAO measurements, combined with upcoming lensing data from the Euclid satellite, launched in July 2023 and returning first science results in 2024, and from the Vera C. Rubin Observatory Legacy Survey of Space and Time, LSST, will measure the matter power spectrum on scales from tens to thousands of megaparsecs with unprecedented precision. If the primordial power spectrum deviates from the inflationary prediction in a specific coherent way on the scales relevant to early galaxy formation, these surveys will detect it. The combination of Euclid's weak lensing, galaxy clustering and galaxy cluster counts with the LSST's deep imaging data will provide a three-dimensional map of the matter distribution out to redshifts above 2 with sufficient statistical power to distinguish between a pure inflationary power spectrum and one modified by the effects of a parent universe embedding. The observational signature of a bubble universe collision in the CMB deserves more detailed examination. If our universe's inflationary bubble collided with an adjacent bubble early in its history, the collision would have deposited energy and momentum asymmetrically from the direction of the collision, creating a disc-shaped region on the CMB sky with enhanced temperature and a specific polarization pattern. The temperature enhancement would be surrounded by a ring of reduced temperature, because the collision would have compressed and heated the plasma in the impact region, while creating a rarefaction behind it. This morphology is distinct from both the random fluctuations of the inflationary power spectrum and from the circular Hawking point signatures predicted by CCC, making the two types of signature in principle distinguishable in CMB data. The WMAP and Planck datasets have been searched for bubble collision signatures by multiple groups, including the teams of Johnson, Pierce, and collaborators. Their analyses placed upper limits on the amplitude of any bubble collision signal at approximately the 1 to 3% level of the CMB temperature variance, depending on the angular scale and morphological model assumed. These limits rule out the most energetic bubble collisions, but do not exclude low-energy interactions that could have subtle effects on the primordial power spectrum without producing a detectable temperature feature. The distinction between a detectable temperature feature and a subtle modification of the power spectrum is important. The latter is accessible only through statistical analyses of the full CMB dataset, whereas the former would appear as a visible anomaly in CMB maps. The fact that no obvious bubble collision disk has been identified does not exclude the possibility that our universe experienced a low-energy interaction with an adjacent domain that modified its initial power spectrum at a level currently below the detection threshold, but within reach of future experiments. The broader class of pre-Big Bang physics, encompassing CCC, string gas cosmology, loop quantum cosmology, and the various multiverse interaction scenarios, shares a common empirical prediction structure. They all modify the primordial power spectrum at large angular scales, low multipoles. They all potentially produce non-Gaussian features in the CMB, and they all alter the predicted relationship between the scalar spectral index and the tensor-to-scalar ratio in ways that differ from the simplest slow-roll inflationary models. The combination of CMB B-mode polarization measurements, large-scale structure surveys, and 21-centimetre cosmology will, over the next decade, provide a multi-dimensional test of this prediction space that can, in principle, discriminate between these alternatives. The scientific program required to answer the question of whether the universe had a beginning is not indefinitely deferred. It is actively underway. Dark energy's role across cycles. Dark energy, the component of the universe's energy budget responsible for the observed acceleration of cosmic expansion, is, within the framework of Lambda CDM, simply a constant energy density of the vacuum, parameterized by the cosmological constant lambda. Its value, approximately 6.9 times 10 to the power of minus 10 joules per cubic meter, is extraordinarily small compared to the theoretical predictions of quantum field theory for the vacuum energy density, which exceed this value by somewhere between 60 and 120 orders of magnitude, depending on the energy scale at which the calculation is cut off. This discrepancy, known as the cosmological constant problem, is arguably the worst prediction in the history of physics, and it has remained unresolved since the accelerating expansion was first confirmed in 1998. Within CCC, the cosmological constant plays a role that is not merely descriptive, but structurally necessary. As discussed in Chapter 8, the positivity of the cosmological constant, its property of driving the universe toward exponential de Sitter expansion, is what ensures that the universe's future conformal boundary, Skiri plus, is spacelike and conformally smooth, a prerequisite for the cyclic transition to the next aeon. In a universe where the cosmological constant was zero, the future conformal boundary would be timelike rather than spacelike, and the CCC transition would not be geometrically possible. In a universe where the cosmological constant were negative, as in anti-de Sitter space, the geometry widely used in string theory research, the universe would recollapse in a big crunch, producing a singularity that would again prevent a smooth, conformal transition. The positive cosmological constant we observe is precisely the value required to make CCC geometrically possible. This is remarkable. The cosmological constant, whose specific value appears arbitrary and inexplicably small from the perspective of particle physics, is exactly the right type, positive, causing accelerating expansion, to enable the cyclic structure of CCC. Penrose does not claim this as proof of CCC, but he notes the consistency. If the universe is indeed cyclic in the CCC sense, then the positive cosmological constant is not a coincidence or a fine-tuning, but a necessary feature of the framework. Universes with zero or negative cosmological constants would not undergo CCC cycles. They would either expand forever without a smooth, conformal boundary or recollapse. The fact that we inhabit a universe with a positive cosmological constant is, in this view, a selection effect. We necessarily exist in an aeon of a CCC cycle, and CCC cycles necessarily have positive cosmological constants. However, recent observations have introduced a significant complication to the picture of dark energy as a simple cosmological constant. The DSI collaboration's first-year results, released in April 2024, measured the baryon acoustic oscillation scale at multiple redshifts using a spectroscopic survey of approximately 6 million galaxies and quasars, covering a redshift range from 0.1 to 4.2. When these BAO measurements were combined with constraints from Planck CMB data and Type 1a supernova data, the best fit model for dark energy showed a hint of dynamical behaviour, specifically a dark energy equation of state parameter W that may evolve with redshift, with a present-day value slightly below -1, the cosmological constant value, and a value above -1 at earlier times. The statistical significance of this deviation from a pure cosmological constant was approximately 2.5 to 3 sigma. Not sufficient for a definitive claim, but suggestive. If confirmed by future DSI data releases and by the Euclid satellite, dynamical dark energy would have profound implications for CCC. A cosmological constant that is genuinely constant, spatially uniform and time-independent fits naturally into the conformal cyclic framework because it produces a cleanly de Sitter asymptotic future. A dark energy that evolves with time, parameterized by the so-called W0WA model, where W equals W0 plus WA times 1 minus the scale factor, might approach the cosmological constant value at late times or might deviate from it, potentially altering the asymptotic geometry of the universe's future. If dark energy ultimately crosses the so-called phantom divide, W equals -1, where it takes values below -1, the universe could eventually end in a big rip singularity, a fate in which the accelerating expansion becomes so extreme that it tears apart all bound structures, including atoms, before the universe reaches a conformally smooth future boundary. A big rip would, in principle, disrupt the CCC transition. Penrose and colleagues have addressed this potential complication by noting that the CCC framework does not require the cosmological constant to be literally constant throughout the aeon, only that the universe's asymptotic future, after all massive particles have decayed and all black holes have evaporated, approaches de Sitter-like behaviour with a positive, effective cosmological constant. If dynamical dark energy converges to a positive constant in the far future, as many models predict, the CCC transition remains viable. If it does not converge, if the dark energy density continues to evolve or diverges, then CCC in its current form would need modification. The relationship between dark energy and black hole evaporation adds another dimension to this picture. In the far future of the aeon, during the era when supermassive black holes are evaporating and the universe's matter content is transitioning from massive to massless particles, the dark energy density remains approximately constant if it is a true cosmological constant, while the matter energy density dilutes as the universe expands. This means that the dark energy's fractional contribution to the total energy budget grows monotonically over time, approaching 100% in the far future. The geometry of the universe in this late era is dominated entirely by the cosmological constant, producing the de Sitter-like geometry required for the conformal transition. The cosmological constant, in this sense, is not just driving current acceleration, it is the physical agent that will eventually clean up the universe, dilute all matter to irrelevance, and produce the smooth geometric canvas upon which the next aeon will be written. The DESI first-year hint of dynamical dark energy deserves examination in the context of the broader history of the cosmological constant problem. The problem has two faces. The first face is the fine-tuning problem. Why is the vacuum energy density so small? Quantum field theory estimates the vacuum energy density by summing the zero-point energies of all quantum fields up to some cutoff scale. If the cutoff is taken to be the Planck scale, the result exceeds the observed cosmological constant by approximately 122 orders of magnitude. If it is taken to be the electroweak scale, the discrepancy is approximately 56 orders of magnitude. Any value short of exact cancellation to many decimal places produces a cosmological constant catastrophically larger than observed. The mechanism by which this cancellation is achieved, or the mechanism by which the effective cosmological constant is driven to a small positive value, is unknown. The second phase is the coincidence problem. Why does the energy density of dark energy approximately equal the matter energy density today? The matter energy density has been declining as the universe expands, scaling as the inverse cube of the scale factor, while the dark energy density is constant, if it is a true cosmological constant. There is no obvious reason why these two quantities, with such different evolutionary histories, should be comparable in magnitude at the current epoch. If we had lived 5 billion years ago, dark energy would have been subdominant. If we live 5 billion years from now, dark energy will dominate overwhelmingly. We appear to live at a special moment when the two are comparable, a coincidence that, in the absence of a dynamical mechanism, requires anthropic explanation. Desai's hint that dark energy may be dynamical, that its equation of state is evolving, is potentially relevant to both faces of this problem. A dynamical dark energy model in which the dark energy density is determined by a scalar field, a quintessence field, rather than a fixed vacuum energy, has the property that the energy density tracks other energy components during certain epochs, naturally producing coincidences without fine-tuning. Whether the DESI signal is robust will be determined by subsequent data releases. DESI is designed to observe 40 million galaxies and quasars over 5 years, with the first-year data representing only a fraction of the total planned dataset. If the dynamical dark energy signal persists and strengthens with additional data, it will require a substantial revision to the cosmological constant picture. A revision with direct implications for the long-term viability of the CCC framework and for our understanding of what drives the universe toward the conformally smooth future that CCC requires for its cyclic transitions to proceed. What the CMB is still hiding. The cosmic microwave background is the most information-dense cosmological observable currently available to science. Its temperature anisotropies encode the acoustic oscillation history of the early universe. Its polarization encodes the geometry of Thomson's scattering at the epoch of last scattering and the presence of gravitational waves from inflation. And its secondary anisotropies, produced by the interaction of CMB photons, with structures that formed after recombination, encode the history of reionization, the distribution of large-scale structure, and the growth of gravitational potential wells across cosmic time. The Planck satellite extracted an enormous amount of this information over the course of its 2009 to 2013 operation and subsequent data analysis, but it was not designed to access all of it. The most significant untapped information in the CMB is in its polarization, particularly at small angular scales and in the so-called B-mode polarization component. CMB polarization is produced by Thomson's scattering of photons of free electrons in the pre-recombination plasma, which generates a quadrupolar pattern in the polarization that encodes the velocity and density fields of the plasma at the moment of last scattering. The polarization field can be decomposed into curl-free E-mode and divergence-free B-mode components. Standard density fluctuations produce only E-mode polarization at the leading order. B-mode polarization is produced by two distinct sources: gravitational lensing of E-modes by the large-scale matter distribution, generating a lensing B-mode signal on small angular scales, and primordial gravitational waves from inflation, generating a primordial B-mode signal on large angular scales, specifically near the degree scale corresponding to the horizon size at last scattering. The current upper limit on the tensor to scalar ratio R, which characterizes the amplitude of primordial gravitational waves relative to density fluctuations, is 0.036 from combined BICEP/Keck and Planck data published in 2021. The Simons Observatory, targeting a sensitivity of sigma R approximately 0.003, will improve this constraint by roughly an order of magnitude, potentially detecting the gravitational wave signal from inflation if R is above approximately 0.01, or tightening the upper limit dramatically if it is below. CMBS4, with a target sensitivity of sigma R of approximately 0.001, would push to even smaller values. If inflation occurred at the energy scale predicted by the simplest GUT-motivated inflationary models, around 10 to the power of 16 giga-electron-volts, then R should be approximately 0.1, already excluded. The non-detection of primordial B-modes increasingly favours either low-scale inflation or an alternative to inflation entirely. For conformal cyclic cosmology, the key observational targets in the CMB go beyond the Hawking point signatures already discussed. CCC predicts a specific modification of the CMB power spectrum at very large angular scales, the quadrupole and low multipole region, because the conformal imprints from the preceding aeon's large-scale structure would preferentially affect the longest wavelength modes of the CMB. The CMB quadrupole anomaly, the observed suppression of the quadrupole moment by approximately a factor of 7 relative to the Lambda CDM prediction, has been present in every CMB dataset since COBE, Cosmic Background Explorer, was confirmed by WMAP and was confirmed again by Planck. Its persistence across 3 independent experiments makes it unlikely to be an instrumental artifact, though cosmic variance, the fundamental limitation on measuring large-scale modes from within the universe, means it can never be more than a 2.5 sigma anomaly purely on statistical grounds. Penrose has noted that the quadrupole suppression is qualitatively consistent with CCC. The conformal imprint from the preceding aeon would modify the large-scale modes in a specific way, potentially producing a suppression of power at the larger scales that mimics the observed quadrupole anomaly. This is not a precise quantitative prediction that has been calculated and compared against the data. It is a qualitative consistency argument. But quantitative predictions are, in principle, calculable within the CCC framework, given a specific model for the distribution of supermassive black holes and large-scale structure in the preceding aeon. And such predictions could be compared against the improved large-scale CMB measurements that future experiments will provide. The CMB's secondary anisotropies, particularly the kinetic Sunyaev-Zeldovich effect and the integrated Sachs-Wolf effect, encode information about the growth of structure from recombination to the present epoch, and are therefore directly relevant to the question of whether the initial conditions of structure formation were those of a standard Big Bang, or were modified by a pre-Big Bang epoch. The kinetic Sunyaev-Zeldovich effect, produced when CMB photons are Compton scattered by the bulk motion of ionized electrons in galaxy clusters, and the warm-hot intergalactic medium, provides a measurement of the product of the electron optical depth and the cluster velocity, a direct probe of structure formation history. Current measurements of the KSZ power spectrum from SPT and ACT are consistent with Lambda CDM, but have large enough uncertainties to permit deviations at the 20 to 30% level on scales below 1 arc-minute. CMB-S4's sensitivity will reduce these uncertainties to a few percent, providing a stringent test of any model that predicts enhanced structure formation in the early universe. The 21 centimetre signal from neutral hydrogen during the cosmic dark ages and the epoch of Reionization represents perhaps the richest and most underexploited source of information about the pre-Reionization universe. The Square Kilometre Array, SKA, currently under construction in South Africa and Australia, with an initial Phase 1 deployment targeted for the mid-2020s, is designed to detect and map the 21 centimetre signal across the redshift range from approximately 6 to 28, covering the full epoch of reionization and the beginning of cosmic dawn. If the initial conditions of the universe were modified by a pre-Big Bang epoch in the way that CCC or multiverse interaction models predict, those modifications would be imprinted in the topology and power spectrum of reionization, the pattern of ionized bubbles, their size distribution, and the timeline of their growth. The SKA's 21 centimetre maps will provide an independent three-dimensional probe of these initial conditions that is entirely complementary to the CMB and to galaxy surveys, and that directly tests the predictions of any model claiming to explain the JWST anomalies. The CMB, in short, is not exhausted as an observational resource. The next generation of experiments, the Simons Observatory, CMB-S4, and the Lightbird satellite, a Japanese-led space mission targeting primordial B modes at angular scales above 1 degree, with a launch targeted for the early 2030s, will extract information from the CMB that Planck could not reach. The B-mode polarization at large and small scales, the lensing potential at high resolution, the spectral distortions from pre-recombination energy injections, and the cross-correlations with large-scale structure surveys. Each of these probes carries potential signatures of physics beyond Lambda CDM and has specific, calculable predictions within both the CCC and multiverse interaction frameworks. The next decade of CMB science will not merely refine the standard model, it will test at the level of statistical significance required for definitive conclusions, whether the Big Bang was a beginning or a transition. What comes after the Big Bang? The convergence of evidence from the James Webb Space Telescope and the theoretical framework of conformal cyclic cosmology does not yet constitute proof that the universe never began, that the Big Bang was a transition rather than an origin. But it constitutes something scientifically significant, a coherent body of observational anomalies that the standard model cannot explain, combined with a mathematically rigorous theoretical framework that offers a unified account of why those anomalies exist. The question now is how science proceeds from here. The standard model of cosmology, Lambda CDM, with inflationary initial conditions, remains the best tested framework in the history of cosmology. Its predictions for the CMB power spectrum, the large-scale structure of the universe, the abundance of light elements, and the cosmic distance scale have been confirmed at a level of precision that no alternative model yet approaches globally. Any framework proposed to replace or extend it must, at minimum, reproduce all of Lambda CDM's successes, while also accounting for the anomalies that Lambda CDM cannot explain. CCC meets this requirement in principle. It recovers a smooth, flat, approximately scale invariant initial power spectrum for each new aeon, consistent with the Planck CMB measurements, while providing a mechanism for the circular CMB anomalies and a principled explanation for the low entropy initial conditions. The multiverse interaction models meet it less fully. They are constrained by, but not yet precisely calibrated to the full suite of cosmological observations. What would constitute a definitive test of the cyclic hypothesis? Several observational paths are now within reach. The first and most direct is the CMB Hawking Point signature. If the Simons Observatory, or CMB-S4, detects with 5 sigma significance a population of circularly symmetric temperature enhancements with the specific angular sizes, temperature profiles, and sky distribution predicted by the CCC Hawking Point calculation, this would constitute strong evidence for a pre-Big Bang epoch. A non-detection at the sensitivity levels these experiments will achieve would not rule out CCC entirely. It would constrain the population of supermassive black holes in the preceding aeon and the efficiency of the conformal transition, but it would significantly reduce the model's evidential support. The second path is the primordial power spectrum. DESI, Euclid, and LSST will collectively provide measurements of the matter power spectrum at a precision that will detect deviations from the inflationary scale invariant spectrum at the sub-percent level over a wide range of scales. If the initial power spectrum of our universe carries specific modifications, enhanced power on scales corresponding to early galaxy formation, suppressed power on the largest scales, or scale-dependent features predicted by the CCC transition, these surveys will detect them. The combination of these measurements with future 21 centimetre surveys from the SKA will provide a three-dimensional map of the primordial power spectrum that is effectively free of the cosmic variance limitation affecting CMB quadrupole measurements. The third path, longer term and more speculative, involves gravitational wave astronomy. The CCC framework predicts that the conformal transition from one aeon to the next produces a stochastic gravitational wave background with a specific spectral shape and amplitude, the gravitational wave analogue of the Hawking Point temperature signature. The Laser Interferometer Space Antenna, LISA, a space-based gravitational wave detector scheduled for launch in the mid-2030s, will be sensitive to gravitational waves in the millihertz frequency band, a range inaccessible to ground-based detectors like LIGSO and Virgo. The stochastic gravitational wave background from a CCC transition would appear in LISA's frequency band if the transition occurred at an energy scale consistent with the CCC framework. Detection of such a background with a spectral shape inconsistent with known astrophysical sources and consistent with CCC predictions would represent extraordinarily powerful evidence.
The question of whether this reorientation is correct cannot be answered by philosophy or mathematics alone. It requires observation. And the observations that will answer it are, for the first time in the history of cosmology, within the reach of existing or near-future technology. We are living at the moment when cosmology is transitioning from a discipline that could only describe the universe to one that is beginning to test whether the universe has always existed. James Webb, pointed at the first few 100 million years of cosmic history, is finding galaxies that should not be there. Roger Penrose, pointing at the cosmic microwave background, is finding circular patterns that should not be there either. Whether these two sets of anomalies are connected, whether they are both symptoms of the same pre-Big Bang physics, different aspects of the same deeper truth about the cyclic structure of space-time, is the central scientific question of the coming decade in cosmology. The universe, it seems, is not finished telling us what it is.